Tungsten is one of the most extreme metals ever used by humans. Unbelievably dense, incredibly hard, and famous for having the highest melting point of any metal. Yet the journey from raw rock to finished tungsten products is far more complex than most people imagine. What starts as ore buried deep underground must be crushed, chemically separated, purified into fine powders, and then formed using specialized high-temperature processes because tungsten cannot be shaped like normal metals. It's the reason tungsten is used in cutting tools, aerospace components, armor penetrators, mining drills, high-temperature furnace parts, and industrial wear surfaces that must survive conditions that would destroy almost anything else. And today on the How Factory, we're going deep inside tungsten production to see exactly how tungsten is made, from ore to one of the toughest industrial metals on Earth. Tungsten's story begins in the 18th century when scientists realized certain heavy minerals contained an unknown element that made them unusually hard to smelt. The name tungsten comes from Swedish words meaning heavy stone, and it perfectly describes the ore's density. As industrial demands grew, tungsten became strategic, especially during the 20th century, because adding tungsten to steel created harder, more heat-resistant alloys. Without tungsten, modern machining and cutting industries would look completely different, because tungsten carbide tools are what allow factories to cut and shape hardened metals at high speed without destroying tools instantly. The process begins at the mine. Tungsten is most commonly found in minerals like Wolframite and Scheelite. These ores don't contain pure tungsten metal. They contain tungsten bound to oxygen and other elements in crystal form. Deposits may be mined using open-pit methods if near the surface, or underground mining if deeper. Ore is drilled, blasted, and hauled to processing facilities where the real work begins. At the processing plant, ore is crushed in stages. Large jaw crushers break rocks into smaller pieces. Then cone crushers and grinding mills reduce them further into fine particles. Tungsten minerals are heavy compared to surrounding rock, so separation relies heavily on density differences. Gravity separation systems such as shaking tables, spirals, and centrifugal concentrators separate tungsten-bearing particles from lighter waste. This produces a concentrate that contains much higher tungsten content than the raw ore, but it still contains impurities and must be refined. After gravity separation, additional cleaning steps may be used. Magnetic separation helps remove iron-rich contaminants, especially for Wolframite ores. Flotation may also be used to separate fine particles by chemical surface properties. The goal is to produce a tungsten concentrate that is pure enough to send into chemical refining. Now the process shifts from mining to chemistry. Tungsten concentrate is transformed into a purified chemical form because tungsten metal itself is extremely difficult to melt and process directly. The concentrate is treated with chemicals that dissolve tungsten compounds while leaving many impurities behind. For scheelite, a common method involves alkaline leaching, converting tungsten into a soluble form. For wolframite, acid or alkaline digestion can be used depending on plant design. The dissolved tungsten solution is filtered to remove solid waste, leaving a liquid rich in tungsten compounds. This solution undergoes purification. Impurities like molybdenum, arsenic, phosphorus, silica, and heavy metals must be removed because tungsten products are often used in high-performance applications. Chemical precipitation, ion exchange resins, and solvent extraction systems are used to pull out unwanted contaminants. The purification stage is slow, careful, and highly monitored. Once purified, tungsten is precipitated into a solid compound called ammonium paratungstate, or APT. This is the key intermediate in most tungsten production. APT forms as white crystalline solids that can be filtered, washed, and dried. A PT is valuable because it is highly pure and can be converted into multiple tungsten end products. APT is then converted into tungsten oxide. Heating APT drives off ammonia and water, leaving behind tungsten trioxide powder. At this stage, tungsten exists as fine yellow or blue oxide powders depending on temperature and reduction conditions. Now comes one of the most important transformations: reduction into tungsten metal powder. Tungsten oxide is placed in high-temperature furnaces where it is exposed to hydrogen gas. Hydrogen reacts with the oxygen in tungsten oxide, removing it as water vapor and leaving behind pure tungsten metal. This reduction happens in controlled furnaces because tungsten powder properties, particle size, density, and purity determine how it will perform later. Temperature, flow rates, and time are all controlled precisely. The result is tungsten powder, a gray metallic powder that looks nothing like the solid metal people imagine. This powder form is crucial because tungsten's melting point is so high that it cannot be cast like steel or aluminum in normal production. Tungsten is shaped using powder metallurgy methods instead. From here, the production path splits into two main routes: pure tungsten products and tungsten carbide products. Pure tungsten is used in applications like high-temperature furnace parts, radiation shielding, aerospace systems, and electrical components. Tungsten carbide is used for cutting tools, drilling bits, and wear-resistant surfaces. To make tungsten carbide, tungsten powder is mixed with carbon black and heated in furnaces to high temperatures. The carbon bonds with tungsten, forming tungsten carbide, an extremely hard ceramic-like compound. Tungsten carbide powder is then milled to control grain size because smaller grains often produce tougher, stronger cutting materials. Additives may be included to fine-tune properties. To turn tungsten carbide powder into usable tools, it must be bonded with a metal binder, usually cobalt or sometimes nickel. This creates cemented carbide, the material used for industrial drill tips and machining inserts. Powders are mixed thoroughly, often using ball mills that grind and blend the mixture into a uniform slurry. The slurry is dried, producing granules ready for pressing. Pressing forms the shape. Powder is loaded into steel dies and pressed under enormous pressure into green parts that hold their form but are not yet strong. These green parts are fragile and must be handled carefully. Some parts are formed using extrusion, injection molding, or cold isostatic pressing depending on complexity. After shaping, parts undergo sintering, the stage where tungsten truly becomes metal-like in strength. Sintering happens in furnaces at extremely high temperatures, often in vacuum or hydrogen atmospheres. During sintering, powder particles bond together, densify, and shrink into solid form. In cemented carbide, the binder metal melts and flows between carbide grains, locking them into an ultra-hard structure. This is what gives tungsten carbide tools their famous strength and wear resistance. Once sintered, parts are extremely hard, so hard that machining them requires diamond grinding tools. Precision grinding shapes cutting edges, drill geometries, and surface finishes. The final dimensions must be exact, because tungsten tools often operate at high speeds and loads where tiny errors cause failure. Pure tungsten parts also undergo sintering and forging processes. Tungsten rods may be swagged or rolled into shape under high pressure. Tungsten wire, historically used in incandescent light bulbs, is drawn through dies repeatedly to achieve extremely thin diameters while maintaining strength. Even this requires careful heat treatment because tungsten becomes brittle if worked incorrectly. Quality control is constant throughout the entire tungsten chain. Chemical purity is tested at the APT stage. Powder particle size is measured after reduction. Sintered parts are tested for density, hardness, fracture toughness, and microstructure. Cutting inserts are inspected for chip resistance and edge quality. Any defect can destroy a tool during machining, so standards are extreme. Sustainability and recycling are increasingly important in tungsten production. Tungsten is valuable and widely recycled from used cutting tools, drill bits, and scrap carbide. Recycling involves chemical recovery or direct powder reclamation, reducing the need for raw mining. This is especially important because tungsten supply is strategically important for many industries. What makes tungsten manufacturing remarkable is how it combines heavy mining with precision chemistry and powder engineering. Tungsten cannot be produced like ordinary metals. It must be purified into powders, reduced in hydrogen, then formed by sintering rather than melting. The entire chain exists because tungsten's extreme properties make it both valuable and difficult to tame. from dense ore extracted from the ground to purified chemical crystals, from hydrogen reduction to powdered tungsten metal, from carbide mixing and sintering to diamond grinding and tool finishing, tungsten's journey is one of the most advanced material production processes in industry. And that is exactly how tungsten is mined, concentrated, chemically refined, reduced into powder, transformed into carbide, pressed, sintered, and finished, turning heavy stone into one of the toughest and most heat-resistant metals on Earth. Thanks for watching The How Factory, where we reveal how the world really works. Don't forget to like, subscribe, and join us again for more deep dives into the materials, machines, and factories behind the world's strongest technology.